All right, Physics 101. Today we are going to be talking about rotational motion, specifically finishing up what we started talking about with torque and discussing when the torques all equal zero. If you hear some background noise, I'm in a train station, so just ignore that and we'll focus on the physics and I'll try to get through it as quick as I can. There will also be an assignment, and I'll talk about that at the end of the video here. So to review, we had certain linear quantities and they had rotational equivalents that, or I guess corollary is a better word. They had a similar quantity but for rotational motion. So for example, for displacement, we had angular displacement. For velocity, we had angular velocity with the Greek letter omega. For acceleration, we had angular acceleration. For mass, we had moment of inertia or rotational inertia. Now, when I get back, we'll talk about different shaped objects and different distributions of mass leading to different moments of inertia. But for the time being, just know that moment of inertia is related to a resistance to a change in how something's spinning. If you have a high moment of inertia, then you have an object that resists any change to whether it's moving, rotating or not. So it's hard to make it start rotating, but it's also harder to make it stop rotating. Force is the thing that made stuff accelerate. Torque is the thing that makes things angularly accelerate. We had momentum, and over here we have angular momentum. We had kinetic energy. We have rotational kinetic energy. So all of the linear stuff that we've talked about has a corollary in terms of rotational motion. They're related terms, but they aren't the same terms. It's really important that we're able to differentiate them. For example, the linear velocity of an object that's going around in a circle, we would say its tangential velocity, the velocity tangent to the circle, is equal to the radius of that circle times its angular velocity times its omega. V equals r omega. Similarly, the relationships that we learned, like for example, V final equals V initial plus acceleration times time. Well, that relationship is still true, but for rotational quantities, omega final equals omega initial plus alpha times t. Displacement, or change in our x value, equals v initial t plus 1/2 a t squared. Well, we can substitute in our rotational quantities and get the same thing. Change in our theta, our angular displacement, equals omega initial t plus 1/2 alpha t squared. And v final squared equals v initial squared plus 2a delta x. Well, we can write omega final squared equals omega initial squared plus 2 alpha delta theta. So all the relationships that we have been using for linear stuff have a corollary in rotational motion. So those relationships are still true. We learned Newton's second law. It said F net equals m times a. Well, tau net equals I times alpha. And this one is one we are going to talk about in pretty substantial detail during this lecture. Momentum equals m times v. Angular momentum equals I times omega. Kinetic energy equals 1/2 mv squared. Well, rotational kinetic energy is going to equal 1/2 I omega squared. All of those still hold. So I mentioned that torque is the rotational equivalent of force, and I gave you Newton's second law, torque net equals I times alpha. Put a pin in that. We'll come back to that in a minute. But we can actually calculate torque depending on how we are applying a force to an object. So let's say I have like a seesaw. It's a board that is balanced on a what we call a fulcrum. We have an axis that it can pivot on. So if I push down on this side, that'll go down and this will go up. And vice versa. If I push down on the other side, that side would go down and the other side would go up. So it would rotate about that center point, that fulcrum, that pivot point. I would apply some force. I'm going to write it in red. I would apply some force at some distance from that pivot point, which would cause it to rotate. And I told you, torque is the thing that makes stuff rotate. So to calculate the amount of torque that is produced by applying a force, it's the cross product of the F vector and the D vector, where D is the lever arm and F is the force applied. I actually I like to use the letter L as a symbol there so it doesn't get mixed up with other length measurements. L for lever arm. Other people use the term R. Dr. Treese, I think, uses the term R for that, or the symbol R. It doesn't matter as long as you know what you're talking about. Torque equals the force applied times the length of the lever times the sine of the angle between those two vectors. So in this case, it's 90 degrees, and the sine of 90 is 1. But if I apply the force at a different angle, like I'll put it in green, what if I apply the force this way? Well, then I would have to take the sine of that angle theta. If I was applying the force directly along that seesaw, that lever that I'm looking at, then there wouldn't be any torque, because the sine of 0 degrees and the sine of 180 degrees are both 0. So that term would be 0, and there wouldn't be any torque. And that makes sense, because if I'm pushing directly along the seesaw, it's not going to go up and down. It's not going to move at all. It's not going to rotate. Or if I'm pulling out, if I'm pulling away like this, then it's not going to rotate. It might slide. It might translate. There might be a net force that causes an acceleration, but it wouldn't rotate. So let's go back to this. If I have a similar seesaw, I'm going to draw another one here. I'll draw it in white. If I have another seesaw and I put a weight on this side and I put a weight on that side, and if they have the same weight and the same distance from the pivot, here's the pivot, so L here and L there, if those are the same, and then the force applied would equal the weight of the objects, so if those are the same, one of them is applying a force that makes it want to spin one way, and the other is applying a force that makes it want to spin the other way. So this one, the green one, would be applying a force that's causing a torque that makes it want to rotate this way. That's the same direction as the hands of a clock. That would be a clockwise torque. And then this one over here, which I'm coloring in red, that would be trying to spin the seesaw counterclockwise. The convention is that counterclockwise is considered positive. But just like everything else, I get to decide what positive and negative is. I just have to stick with it through my problem. But most of the time, when you're dealing with physics problems, people treat counterclockwise as positive, just like most of the time we make up positive. And most of the time we make right positive. But sometimes it makes more sense to go the other way. Still, the convention is the counterclockwise direction is the positive direction, and the clockwise direction is the convention is the negative direction. In this case, the clockwise torque, the negative, and the counterclockwise torque, the positive, would be the same because they both have the same force, they both have the same lever, arm distance, and they both have the same angle. So if all of those are the same, then the positive torques and the negative torques would add up to 0. So in this case, the net torque, tau net, would equal 0, which means I times alpha would be 0. That's this equation up here. And if I times alpha is 0, that means it's not accelerating rotationally. It's not going to rotate. It's balanced. We have reached an equilibrium. So the next slide we'll talk about that term. What is a static equilibrium? So I'm going to just redraw that same seesaw. We got our pivot point here. We got our red weight with some mass, and the force equals m times g. Then we got our green weight over here with an m, and m times g on that side too. And it's going to have a lever arm like that, and this one's going to have a lever arm like that. And if all of those happen to be equal, if it just so happens that they end up being equal, then we know the torque is the same. They don't have to be equal for the torque to be the same. If I had a bigger mass on the green side and it was closer to the pivot point, we could still have the same torque, right? If I have torque equals F times L times the sine of theta, if the F is bigger but the L is smaller, we can still end up with the same amount. But in this case, they're all the same, just to make our lives and our conceptual understanding easier. So in this case, we know that tau clockwise equals tau counterclockwise. So the net torque, tau net, is equal to 0 Newton meters. Also, we have 2 downward forces, and we are going to have 1 upward force. The pivot point is holding up this seesaw. The normal force, Fn, or F from the pivot point. Fn is going to equal the downward force. The downward force from the red plus the downward force from the green. The net force, F net, is also going to equal 0. Because it's not accelerating up, it's not accelerating down, it's not accelerating left, it's not accelerating right. So the net force is 0, the net torque is 0. And when the tau net equals 0 and the F net equals 0, then we have a static equilibrium. So that's a really important case, especially for engineers who have to build things like bridges or skyscrapers or things that we don't want to accelerate. We don't want our bridge to suddenly accelerate rotationally, because that means it broke and is falling into the river. So that's bad news. We want to make sure that we establish the conditions such that a static equilibrium can be maintained. So there are lots and lots of examples. A flagpole holding up a flag is a static equilibrium. A sign hanging in front of a shop. A bridge, a drawbridge pulling up the doorway that lets you in, or really any bridge, is a static equilibrium. A couple other things about this diagram. So normally a free body diagram you just treat as a point mass, but when we're dealing with torques, where the forces are applied matters. So we have to draw what's called an extended free body diagram that shows where the forces are applied, like the one I drew here. So in this case, we show where the masses are applying their force. We show where the fulcrum, or the pivot point, is applying its force. And by showing where those forces can be applied, we get to choose a pivot point location and calculate the torque from wherever, from any of those. Now, I think it's important to note that in a static equilibrium situation, you can pick any pivot point. It doesn't have to be. So in this case, this blue spot right here is the pivot point. Physically, that's where the seesaw would rotate. But I can choose any point on here that is convenient for me and use that for my pivot point and measure from that and still get the net torque from that spot to be 0. It's convenient to pick that middle point as our pivot point, 1, because it is actually where it's pivoting, but 2, it eliminates one of the forces causing torque. So if I just picked some random spot, there would be 3 forces that have some distance from the pivot. But if I pick the actual pivot point, the fulcrum is where it's holding it up, that force is a lever arm of 0. So it doesn't add a torque into our torque equation. So when I'm calculating the clockwise and the counterclockwise torques, I have one less torque to worry about. So it's a convenient spot to pick. All right, let's do a quick example. And then I actually want to do one from the homework that isn't about this, but it was a little tricky, so I wanted to just help you set it up. And then I'm going to talk about the assignment. So let's say we have a pole with a cable on it, and there's a bar that the cable is holding up, and then there's a sign hanging from the end of this pole. So it's a sign with some mass. So the sign has a mass of M. The pole has a mass of, we'll say, big M. There's a cable holding it up. So in this case, there are there are going to be 4 forces that we need to consider. There is the force of gravity of the sign pulling down. There's the tension of the cable pulling up at some angle theta. There is the weight of the flagpole pulling down. And there is the wall applying a force holding the pole up. So this is my extended free body diagram for this scenario. So it's important to note that the weight of the pole acts at the center of mass. So if it's a uniform pole, the center of mass is going to be right there in the middle. And that's where the force of gravity is going to be pulling down, with the force of mass of the pole times g. And the sign is going to pull down with a force of the mass of the sign times g. The tension, in these kind of problems, usually it's asking something like, what is the tension? And you'll know like the angles and you'll know the masses. It could also ask, what is the force from the wall holding it up? That could be another question it asks. You'd approach them both in a similar way. We know that this is a static equilibrium, so we know that the clockwise torque is going to equal the counterclockwise torque. We know that the force up is going to equal the force down, because the net force is 0, the net torque is 0. We know that the force to the right is going to equal the force to the left. So each of those gives us an avenue to understand what's going on. Looking at the torques, we have to pick a pivot point. And in this case, there's a really convenient pivot point, especially if we don't know the force of the wall holding it up. If I choose this green spot right there, the connection between the pole and the wall, as my pivot point, then that force doesn't add either a clockwise or a counterclockwise torque. It's acting right on the pivot point, so the length of the lever is 0, so there is no torque from that force from the wall. So instead, when I'm doing my net torque calculations, here I'm going to erase that to make a little bit of space. My net torque calculations, my clockwise torque would come from the weight of the pole and the weight of the sign. So T pole plus tau sign would equal the counterclockwise torque, which would be tau from the tension. In the case of the downward forces. They both make a 90-degree angle. So the sine terms they just drop off. They become 1. Sine of 90 degrees is 1. So torque is going to be the force applied, which is mg, times the lever arm, which would be 1/2 the length of the pole, plus, for the sine, the force is its weight, which is lowercase m times g, times the length of the lever, which is the length of the pole. That would equal, well, we would have to be given in the problem where this pole connects, or where the cable connects. So we'll use that as a lowercase l as that. That would be a given in the problem. The tension we don't know. That's something we would be trying to find. Tension would equal, tension is the force, times the length of the lever, times the sine of that angle. That would be given as well. So with all of that information, we would know the mass, we would know the length of the lever, length of the pole, we would know the mass of the sine, and we'd know the length of the pole. And we would know, as I said, where it's connected, and we know the angle. So the only thing we don't know, the only thing that is an actual unknown that we can solve for is the tension. Awesome. Once you have the tension, then we can look at the force equations and figure out the force from the wall holding it up. If the up force equals the down force and the left force equals the right force, let's start with this one. Let's start with the left and the right. The force to the right, well, there's only one force to the right. That's the x component of the wall force. So F of the wall in the x direction would equal the force to the left, and there's only one force to the left. That would be equal to the tension in the x direction. They're equal but in opposite directions, right? One is positive, one is negative, because they add up to 0. So if I took force of the wall plus force of the tension, both in the x direction, added them together, I would get 0. Because one's going right, one's going left. So if I found the tension using the torque equation, and I know the angle, I can use a little trigonometry to figure this out, and then that would give me that number. The up and down works the exact same way. What forces do we have going up? We've got the wall force going up. We've got the tension force going up. What forces do we have going down? We've got the weight of the pole going down, and we've got the weight of the sine going down. From that, we can find the F in the y direction. And once we have both of those, we can figure out that force. So that's a lot, and I'm trying to go fast because it looks like my train is arriving at the station. But we're going to do a whole bunch of these problems. I just wanted to give you an overview of sort of how they look and what the process is, what the process we're going to go through. As a whole, we're going to look at the torques, and we're going to know that the net torque is 0, so the clockwise torques equal the counterclockwise torques, and that's going to give us some information. We'll also know that the forces will add up to 0, so the ups and the downs will be equal to each other, and the lefts and the rights are going to be equal to each other, and that's going to give us more information as well. All of those are ways to figure out any of these bits and pieces that I mentioned. They all fit into one of those categories, and knowing that we're in a static equilibrium is a window into using these equal torques and equal forces to solve problems. So I guess that's actually a good segue to tell you about your assignment. For your assignment, what I would like you to do is find an example of a static equilibrium. It can be a hanging sign somewhere, it can be a bridge, it can be anything. You can look it up on the internet, just find one. Ideally, if you find one, you can take a picture of it and share it, or you can, as I said, look one up on the internet and find it. And I'd like you to draw an extended free body diagram, just like the one that I just showed you on that last portion. I don't expect you to be perfect at that. We haven't practiced. It's your first try. But I would like you to make that free body diagram and record yourself doing it. You could do it on an app like what I'm using. There's a bunch of free apps that you get to record yourself drawing on a tablet. or you can actually just hold your phone up and record yourself putting it on a piece of paper. Any of that would work. Well, my train got delayed, so I have a little bit of extra time, which allows me to switch gears a little bit, slow down a little bit, and help you with this question from the homework. I think this is one of the trickier ones from the homework, so I wanted to help you at least get it set up. We have a stunt pilot performing a loop-de-loop in a vertical circle. We're given the radius of the circle. Ooh, hey, got to put the pen on, and we're given the radius of the circle. We're given the weight of the pilot, and then we're given the speed of the plane. So it says, at its highest point, determine the apparent weight. What we're actually trying to find when we're looking for apparent weight is the normal force. So we want to find the normal force. At the top, there is, on the pilot, the force of gravity pulling the pilot down, but also the seat of the plane providing a normal force that is making that pilot go in the same circle that the plane's going in. So that's what we're actually trying to find. We know that F net equals M times A. And in this case, there is no upward force. So we have two downward forces. And we are actually going to get an acceleration that's making the pilot go in a circle. It's going to be a centripetal acceleration. So I am going to call, for this first part, for part A, I'm going to call positive towards the middle of the circle, which is going to be, in this case, down. Down is towards the middle of the circle, because that's the direction the acceleration is going to be. And the forces and accelerations are going to be in the same direction. So I could call both of those things negative if I wanted to. I think it's just easier if I call them both positive. I don't have to worry about negative signs in the problem. So F net is going to be the sum of the forces. So we're going to have the force of gravity plus the normal force, and that's going to equal the pilot's mass times the acceleration, which is v squared over r. That's the equation for centripetal acceleration. That right-hand side just turns into the centripetal force equation, mv squared over r. So there's two issues here. One, we're trying to find the normal force, so we're going to have to solve for that. And two, we don't know the mass, but we do know the weight, and we know that the weight is the force of gravity, which equals m times g. So the mass is going to be that force of gravity, which is given in the problem, divided by 9.8. So we can find the mass easy enough. And the mass is going to be the same in all three parts of this problem. The other part's not too hard either. I just have to solve for Fn. So Fn is the normal force, which is going to equal the apparent weight. That's going to equal mv squared over r minus fg. So in order to find the answer for part A, I got to find the m and then plug it into this equation right here, where v squared is given in the problem, v is given in the problem, then we square it, r is given in the problem, and fg is given in the problem. The next part says, at what speed would the pilot experience weightlessness? So weightlessness means that the apparent weight is zero. So with everything else being held constant, I set Fn equal to 0 and solve for the velocity. So now I know the mass, I know the r, I know Fg, and I know that the normal force equals 0. I'm going to solve this equation for velocity. So that's part B. So this is part A, this is part B. For part C, we're looking at the bottom. And at the bottom, the gravitational force, Fg, is pushing down, and the normal force, Fn, is pushing up. At the top, your weight is taking away from the normal force you feel, so your apparent weight is reduced. But at the bottom, your weight is adding to the force necessary to keep you moving in that circle. It's pulling you down while the seat is pushing you up, so it requires more force from the seat in order to keep you moving in that circle. So we know your apparent weight is going to be bigger. It's like when the elevator is moving up, when it's accelerating upward, you feel heavier. When it's slowing down or when it's moving downwards, you'll feel lighter. So it's the same kind of relativity type of classical relativity that we've done in the past. So for part C, it's kind of the same deal. The net force, like we did up at the top, like up here, the net force equals m times a. We still have an acceleration, a centripetal acceleration, but now Fn is up and Fg is down. So Fn is towards the middle and Fg is in the opposite direction, so it's going to be minus Fg equals mv squared over r. And we're given the velocity, we're given Fg, we're given m. We just have to solve for the normal force. So Fn is going to equal mv squared over r plus Fg. All right, so that's how you set it up. If you run into any trouble or if you need any extra help, feel free to send me an email. I will be available. I will be at a conference for the next couple days, but I'll be checking my email regularly, and I'm happy to help you when I'm not at a train station. So let me know, and have yourself a great weekend.